Okay, hi everyone. We are the 2018-2019 Boeing scope team, and this year we were working on improving the wire harness assembly process. You've probably heard of Boeing, but if you haven't, can we make that bigger? Boeing is the world's largest aerospace company, and it's a leading manufacturer of commercial jetliners and defense, space, and security systems. I'm Sarah Ballantyne, this is Audrey Lewis, and Carl Moser and Alex Scott. With the increasing complexity of modern aircraft, the quantity and complexity of wiring within each aircraft has increased dramatically. Wires are used for a wide range of systems on board each aircraft, such as aircraft control systems, onboard lighting, individual passenger media consoles, and even personal charging. Complex wire harnesses, combined from thousands of individual wires, are assembled by hand by skilled technicians at Boeing. In order to gain a sense of scope for this project, there are about 45 Boeing 737s produced each month. In each Boeing 737, there are 25,000 to 75,000 individual wires. Each of these wires connects to a connector, and we have 3,000 to 9,000 connectors per aircraft. These wires must be identified at many steps throughout this process, which is a huge task. Knowing that this wire identification took a long time, Boeing came to Olin with the task to develop new technologies that aid manufacturing workers to improve speed and accuracy in order to streamline the wire harness assembly process. Our goals this year were to develop a handheld or wearable wire identification tool and deliver functional prototypes to Boeing. These prototypes would be usable on the production floor. In addition, we were asked to deliver a manufacturing package for our device to ensure repeatability for mass production later on. Towards that end, this is more specifically the product that we designed and developed with Boeing this year. Our product is a lightweight, battery-powered, highly portable device used by assembly technicians. It captures a view of all sides of the inserted wire. It interprets the wire IDs from those images using optical character recognition and onboard image processing. And finally, the device transmits these wire IDs to a base station that is already connected to the Boeing existing systems. Benefits we anticipate from the implementation of this device include reducing errors due to wire misreads, improving the ergonomics of this assembly task, and finally, speeding up this assembly task responsibly. In order to get to the point where we had fully functional prototypes at the end of the year, we split our process into 5 key steps. First, we came up with preliminary designs. We then took those designs to Boeing, and we did user research and co-design. From there, we worked to demonstrate all of the key technologies needed for these devices. We developed functional prototypes, and finally, we continued into the design and manufacturing space and the product handoff. At the beginning of the year, we made a few key design choices. First, we predicted ergonomic requirements, such as a lightweight, flexibility, and ambidextrous use. These requirements at this stage in the production design led us to a 2-part product design with a hand unit and a unit connected to via cable that rested on the arm. We determined at this stage that all of the image processing should be done on board our device. This led us to the conclusion that the hand unit should contain the optical equipment and the arm unit should contain all of the computational equipment. We developed an InterAx-like model for user testing and co-design. This model demonstrated the form factor and product interaction that the users could expect. This included how to load the wire and also what the device would indicate in response. The model was then brought to Boeing, as you can see here, and we used it in user interviews and in test interactions with these production technicians. We received valuable feedback at this point on the ergonomic requirements we had proposed earlier. These interviews also brought to light the importance of user comfort during long-term wear and the importance of customization for each step of the manufacturing process. Additionally, these interactions led us to mechanical design decisions, such as our method of wire retention within the device. The next step in our process was to develop and demonstrate these key technologies that we would need for a successful product. These technologies included the ability to capture and transmit information from the full wire circumference at a reasonable scan speed. In addition, we aim to demonstrate that the wearable, size constraints, and ergonomic restraints were actually feasible. We developed test platforms in-house for our optical, mechanical, and software subsystems, and performed iterative testing on each system. Our final design was selected early this spring semester, and work began on our functional prototypes. Our functional prototypes were assembled and programmed in-house. We used a combination of commercial off-the-shelf components and custom components for our prototypes, while developing plans for later mass manufacturing. At the current stage of the process, our prototypes and designs have been handed off to Boeing and its affiliates. Prototypes will then be tested with production technicians, and the design will be refined. By next year, the devices are predicted to be in a state ready for manufacturing and for use at the Boeing facilities. Finally, we wanted to thank everyone who contributed to our team this year, especially our liaisons, Bradley, Andrew, Grace, and Damien, our advisor, Alicia, and all of our subject matter experts, with a special thank you to Lauren, who really was our 5th member of the team. Thanks.